So in this video we'll be discussing the application of shell balance approach in heat transfer and mass transfer systems. So let's get on with it. So for all physical systems, either in Cartesian coordinate system, in spherical coordinate system, or in cylindrical coordinate systems, the steps required to execute spherical shell balance approach are same. First, we'll have to select a thin element. In Cartesian coordinate system, that would be a thin sheet of thickness dx. In a cylindrical coordinate system, it would be a thin spherical shell of thickness dr, and similarly in a spherical coordinate system also it would be a thin spherical shell of distance dr, of thickness dr and distance r from the center. So the first step is done. We have defined an infinitesimally small element of required thickness and its geometry depending on the coordinate system. The second step would be to apply conservation equations like either energy balance in case of heat transfer systems and material balance in case of mass transfer systems. So the basic energy conservation equation is rate of input minus rate of output plus generation is equals to zero. Zero is the term of accumulation. We assume steady state in all our assumptions. So accumulation is zero in case of steady state. The third step would be the equation we will get from the energy or the material balance conservation. We will have to use a governing law to substitute the required quantity in there. So in case of heat transfer, we will use Fourier's law of conduction, and in case of mass transfer, we will use Fick's law of diffusion. After substituting those expressions into the conservation balance equation, we'll get a second order differential equation in terms of the quantity whose profile we want. So like in case of heat transfer, we'll get a second order differential equation in temperature, and in case of mass transfer we'll get a second order differential equation in concentration. The final step would be to integrate that and get an expression for T or Ca and use boundary conditions to eliminate the constants of integration that are present in the equation due to double integration. So boundary conditions would either be given in question itself, or we'll have to use logical assumptions to eliminate the integration constants from our system. So this is an example of energy conservation in rectangular coordinate system, and as you can see, we have used Cartesian coordinate system. So constraints we have used is assumptions, steady state system, hence accumulation is zero, and 1D conduction. That's why it's in Cartesian coordinates. The heat is only traveling or changing in the x direction. No heat generation. We are not assuming any generation of heat in this lab, and we have assumed the thermal conductivity of this material to be constant. Now, using energy balance equation, we'll use rate in minus rate out is equals to zero. That would be rate in is equals to rate out. As we assume steady state, there will be no accumulation term as well as no heat generation term. So at the input there is qx, that is heat input, that is rate in, and at output that is qx plus dx. Now qx plus dx is this, that is qx plus the rate of heat transferred from this slab to the surrounding through convection. So that is the expression for that, and on simplification this will get cancelled out. So dqx by dx equals to 0 would be the final expression we get. Since this is equals to 0, hence we can say that the flux qx is constant, as differentiation of a constant term is 0. Thus flux is constant across the slab. That's what written over here. Now we'll substitute qx is equals to minus k dt by dx. That is the Fourier's law of heat conduction, and we'll get a temperature profile on integrating that particular expression. So as you can see, this is our Fourier Taylor's law, Qx is equals to minus k dt by dx. Substituting this in our previous equation, dqx by dtx. So, we have assumed thermal conductivity of the slab to be constant, so it will come out, and there will be double differentiation of the temperature with respect to x. d square d square t by dx square, that is a typo here, is equals to 0. On integrating it two times, we'll get an equation for temperature. So double integration yields T is equals to C1x plus C2. Now C1 and C2 are constants of integration, and to eliminate these constants we'll have to use boundary conditions. Boundary conditions are the conditions that are on the boundary of the system. So like at x equals to 0, that is a boundary. So it's given that at x equals to 0, the temperature is T naught, and the other boundary is the right hand side. So at x equals to L, the temperature is TL. Using those boundary conditions, at x equals to 0, T equals to 0, this term will get cancelled and C2 will be equals to T naught. That's what written over here. Now substitute C2 is equals to T naught in this equations. Now at x equals to L, we know T is equals to TL. So TL is equals to C1 into L plus T naught. The C1 will be equals to TL minus T naught by L. That's written here. Substituting C2 and C1 back in this equation, and we'll get our final output. T is equals to T naught minus TL into x by L. That is our concentration profile that we can write across the slab's length. And if we want a total heat rate, so that was flux, basically qx is flux is heat generated per unit heat supplied per unit area. So if we want total heat rate, we'll have to just multiply flux with area. So flux was k T1 minus T2 by L. Just multiply it with area A, that is the surface area of the slab. So we'll get total heat rate Q is equals to Ka T1 minus T2 by L. Now, a very popular analogy that is used for heat transfer systems, especially walls, that is thermal resistance, Ohm's law analogy. So, as we know, rate is driving force by resistance. That this term is similar to the term we've used in Ohm's law. V is equals to IR, or I is equals to V by R. To rate here is the current, V is the driving force, and R resistance is the thermal resistance offered due to the walls. So let's suppose a solid wall that is squeezed in between fluid A and fluid B. Fluid A has some thermal properties, fluid B has some thermal properties. Heat transfer from solid wall to B and solid wall to A would occur via convection. So, and a solid wall will have a conductive resistance. So, if we use these resistances in terms of the Ohm's law analogy, so we'll write L upon Ka, that is the length L, total length of this wall, upon K. K is the thermal conductivity of this wall, and A is the cross sectional area of this wall. So, using the electric current analogy, resistance is length upon conductivity into area. So, that's basically it. Similarly, for fluid A and fluid B, we have convective resistance. In case of convective resistance, instead of thermal conductivity K, H is used. So 1 upon H into A. A is again A is again surface area of the wall or surface area of this particular material. Now, the total system, finally what it will become. So rate is basically Q, rate of heat transfer or current, if we talk about Ohm's law analogy, is equals to Ta minus Tb by R total. Ta minus Tb, that is driving force, that is delta V basically, and R total means total resistance offered by the system. So as we can see, this is resistances connected in series or composite wall system. So our total would be summation of this plus this 1 upon HA into A, that is for fluid A, L upon KA into A, that is for solid wall, and 1 upon HB into A, that is for fluid B. Keep in mind these A are surface areas, not associated with fluid A. Now let us solve a numerical based on that. So that this is a numerical composite wall analysis. So basically we have a brick wall. After that we have an insulation, and after that we have a layer of air. Layer of air, basically it is surrounding. So imagine a brick wall and some paint or coating is applied on it, that is acting as an insulation, and then this is the surrounding ambient. So heat supplied to the wall was 400 watt per meter square. The dimensions and thermal conductivities of all these materials are given. Using the electrical circuit Ohm's law analogy, we can assume this as an resistance, this as a resistance, and this as a resistance. The length of this wall is zero point 0.5 meter, length of insulation is zero point 0.3 meter, and the surrounding it would be infinite. That's why the end temperature would be T infinity. Infinite as compared to these two lengths. Now, solving for outer surface TR. If we want to solve for TR, so using a convective heat transfer formula, that would be Tr minus T naught is equals to Q naught by H. Driving force is equals to I is equals to V is equals to IR basically. So TR is equals to T at ambient temperature. Ambient temperature would be 25 degrees centigrade. We have used that here. Heat supplied was 400 watt per meter square, and H is given 20 watt per meter square Kelvin. So substituting 20 into 20, that's 400, 25 plus 20, that would be 45 degrees centigrade. Thus the temperature of TR is 45 degrees centigrade. Now solving for the inner surface TL. So for TL, we'll again use the same formula, but instead here we used only one resistance, that is 1 by H, because there was only one resistance offered between TR and T infinity, and that was the resistance offered due to air. Now between TL and T infinity, there are three resistances. One is offered by the brick, one is offered by the insulation, and one is offered by the air. So we are using all three resistances, and we if you will notice, we have substituted the area term here. Why? Because Q naught in the previous slide, if you will see, this is Q is rate, and here it is Q naught. Q naught is basically Q by A, that is flux, and we have been given flux in this question. Thus we have taken area common and divided it by Q. Thus we have got this Q naught, that is flux. So substituting the values that we have been given in this question, LA 0.05, LB 0.03, H20, KB 0.06, Ka1, and on solving we'll get the temperature of inner surface, that is TL, is 265 degrees centigrade. Now another shell balance derivation, and this one is for mass diffusion or mass transfer. So this, as you can see, this includes a coordinate system spherical coordinate system. So mass diffusion in spherical systems, constraints or assumptions is of course steady state. Then radial diffusion only, the diffusion that will occur in the direction of this r. That is the characteristic property of the spherical coordinate system. Then isothermal system, so no temperature changes there, and no bulk flow. We have neglected the bulk flow. Unlike a flat wall, the area availability for transport expands rapidly because we have assumed radial diffusion. So the amount of area for diffusion will increase radially outwards, and it will increase with r raised to the power 2. So surface area for diffusion would be 4 pi r square, and area increases with r, thus flux must decrease outwards. So if we draw a graph, and at increasing r, the flux will always decrease because the amount of area is increased. Since flux is rate per unit area, if denominator will increase, area will increase, the flux would always decrease. That's what is written over here. Now, using the shell balance approach, let's apply material balance over this spherical shell. So we have assumed a shell of radius r having thickness dr in this sphere. So Na is the rate of mass transferred. So let us assume that Na is the rate of mass transfer supplied. A is the surface area. Na is basically flux, and A is the surface area. So rate would be flux into surface area. So 4 pi r square into Na minus 4 pi r square into Na plus. So this is the diffusion term, d by dr into dr, minus this is the generation term. So if there is a chemical reaction occurring, assume A to B of rate constant K. So we will use KCA into surface area into dr. Substituting this, dividing by 4 pi r square, we will get minus dna by dr minus kca is equals to 0. Now remember this equation because now we will have two cases. Case 1 would be with no reaction. In no reaction, this term will get cancelled and we will only have minus dna by dr. Case 2, we will have a chemical reaction and this term would still be there. So let us see. Substituting Fick's law here, Na. So we know Fick's law says that Na is equals to minus ka dAb into dCA by dr. dAb is the is the diffusivity of A in B or B in A. dCA by dr, that is Fick's law. Now substituting that over here. So multiplying and dividing by r square. In this term, if you multiply and divide by r square, so 1 by r square, and then send this r square into the differential. So 1 by r square d by dr, r square into dca by dr, this term, minus k, that dab that was over here is also divided by the whole equation. So dab is here and here it would have been 0. So this term accounts for the mass consumed by chemical reaction in the generation of product. This term accounts for the diffusive transport of the required quantity, and this term accounts for the expanding spherical geometry of the system. So impact of reaction kinetics on concentration. This is with no reaction. No reaction, as I said, this term will get cancelled out, so we will have only this term. So d by dr of r square into dca by dr is equals to 0. On integration, this yields ca is equals to minus c1 by r plus c2. Again, boundary conditions will take care of these c1 and c2, and will get concentration profile Ca. Profile is inherently non-linear strictly due to spherical geometry. In case of with reaction, so this term Ka by dAb is substituted as m square, and this is written like this. And when you integrate it using hyperbolic trigonometric substitutions, integration will yield Ca is equals to a After applying boundary conditions, A into sin h mr by r. Again, m here would be m is equals to under root k dab, or m square is equals to k dab. The reaction further increases curvature, creating maximum resistance at the center of the curvature. So at the center of this spherical particle, the resistance for diffusion would be maximum in case of with reaction. System application, again this is a question. So assume a spherical catalyst palette, and at some distance from the palette we have to identify the concentration of A. So this palette is of radius r. Boundary conditions are given as at bulk, or in middle of this CA is equals to CA infinity at bulk of A. At bulk of A means at the surrounding, at infinite distance from this particle. CA is equals to CA infinity, that is concentration of A. At surface of this particle, R is equals to capital R. Flux meets reaction rate. So Fick's law would be used, and Na would be Ks into Ca, that is rate generated by a chemical reaction. And we have to derive this formula: Ca by Ca naught is equals to 1 minus delta, uh, and where delta square is Ks into R by dV. And another thing which we have to derive or show or prove is rate is equals to area into Na, and this would translate to this. So let us see how we can do that. This is a comparison between Cartesian heat conduction and spherical mass conduction. Observed entity in Cartesian heat conduction is energy heat, of course. In spherical mass diffusion, it is mass, of course. Geometry: Cartesian coordinate system uses constant area dx. It is comparable to a flat one. And in case of spherical mass diffusion, it is comparable to a sphere because of expanding area. Driving force in case of heat conduction: temperature gradient dt by dx is the driving force, whereas in case of mass diffusion, concentration gradient is the driving force, dca by dr. Rate law in case of heat conduction, as I said, Fourier's law of conduction is used, and in case of mass transfer, Fick's law of diffusion is used. System flux is constant across the wall in case of Cartesian coordinate systems, and in case of spherical coordinate systems, decrease outwards radially. So that was all from my side. Thank you.